So welcome back in once again in the second lecture of, or you can say third lecture, because first was the very introductory. There is a discussion of the syllabus only. So today we are going to discuss the type of signals. So first type of the signal is continuous in time and continuous in value. Continuous in value. Basically, there are only the four category of the signals. Now, another signals are all the signals are derived from these four signals. Okay, so what is the continuous in time and continuous in value? Simple definition is, it is a very simple definition, continuous in time and continuous in value. It is defined at each and every instant of time. It is defined at each and every instant of time, and it can attain, it is defined at each and every instant of time and can attain any value. It can attain any value from positive maximum to negative maximum. Okay, this is a graph of sin t, you know very well, sin t, and let's say this is the xt is equal to the sin t. So sin t, it is defined as each and every instant, each and every instant, each and every instant of time, defined at defined at each and every instant of time, first thing. And second thing, it can attain any value from positive maximum to negative maximum, right? Negative maximum, it can attain any value, it can attain any value from positive maximum to negative maximum. This is the continuous in time and continuous value. Now up come to the second type of the signal, that is the continuous in time and discrete in value. Continuous in time and discrete in value. So what is the continuous in time and discrete in value? It is very easy. Continuous in time and discrete in value is nothing but looking like this signal. It is defined. So what is this? This is, let's say, xt, and this is the t. So the concept is, it is defined at each and every instant of time, but it can attain it can attain only it can attain only some discrete value. You can see here some discrete value, some discrete value discrete value. Here you can see either the value is the positive maximum or the negative maximum, or at this point this is the discontinuous. We'll discuss later why this is the discontinuous. But here you can see from this figure, either the value is positive maximum or the negative maximum, nothing else. Okay, from this point to this point, this is defined as a positive maximum. From this point, from particular this point, the value is negative maximum. Again, this is a positive maximum, and so on. So this is the value is discrete, time is continuous. The defined, it is signal is defined at each and every instant of time. So this is a continuous in time, but the discrete in value. Now the third type of the signal is discrete in time and continuous in value. Third type of the signal is discrete in time and continuous in value. What it means? It means, remember, whenever, let's say we have a continuous signal in time and value, both time and value both. Let's say this is the xt signal, and this signal is converted into like this. Let's say we have, it is defined as, it is defined not in the continuous but in the discrete. So how this is defined? How it is defined, you can say this is defined like this one. This is defined like this one. So I think I have made wrong. Okay. So this is the, sampled. This signal is known as the sampled signal, the sampled signal. It is very popular signal, very, very popular signal. This is a sampled signal. Signal is the same, but in now defined in the discrete time, not in the continuous time. It is defined here, 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 here. Now it is converted to the discrete time. It is defined in the discrete of time, but the value can attain any value, either the positive maximum or in the negative. It can attain from this value to this value. It can attain any value, right? So the technique is the conversion of this signal into this signal is sampling theorem. We will cover and we will study this theorem in detail, more detail in upcoming lecture. Sampling. So sampler or sampling theorem is, the technique by which we can convert, we can enter from the analog to digital world, right? This is the techniques by which we can convert the analog signal to discrete type of the signal, right? So the last signal, so how it is defined? It's defined at the discrete instant of time. It is defined at the discrete instant of time, but the signal can attain, but the signal can attain any value from positive maximum, okay, to negative maximum, right? So you can say all the sampled value, right? All the sampled value, or you can say all the sampled signal, all the sampled signals are discrete. It is very, very important. Discrete in time and continuous in value. Remember, remember always. So now now the question is, if we are able to convert this discrete value into some discrete value, some continuous value, sorry, this continuous discrete in time and continuous discrete, sorry, discrete in time and continuous, discrete in time and continuous, discrete in time and continuous value, if we are able to convert it into discrete in time and discrete in value, then the signal becomes automatically the digital signal. Okay, so how it will cover? You can see the fourth type of the signal. The fourth type, the category of the signal is nothing but it is defined as a discrete in time and discrete in value. Discrete in value. So how it is defined? It is nothing but the xt signal, the signal xt, whenever is sampled, whenever is sampled, you can now understand this sample signal is converted into the DTCV, discrete in time and continuous value. This is the CTCV, sorry, CTCV, continuous in time and continuous value, is converted into the discrete in time and continuous value with the help of sampling theorem. Then the one technique is used, that the quantization. I will let you know what is the quantization. So the quantized value, then this quantization, what will do? This quantization is convert this DTCV into the DTDV, discrete time and discrete value. And finally, the discrete time and discrete value is encoded. Encoded, what are the encoding? Why we are going to use the encoding signal? I'll let you know. So again, this signal becomes finally the digital signal. Okay, finally the signal becomes digital. So now there are two questions arises here. What is the quantization and why that is encoding? So before going into detail, I am repeating, the discrete in time and discrete in value signal are the sampled quantized sampled signal. Sampled quantized signal are the discrete in time discrete value, and then discrete in time discrete value is converted or encoded, and that final signal is the digital signal. Okay. So question is, what is the quantization? Quantization. So nothing. Quantization is, the digitization of analog signal. You can say the digitization of analog signal. Digitization of analog signal. Okay, involves, there are some techniques. First technique is rounding off. Rounding off, right? So rounding off of the values, okay, value which are approximately equal to, which are approximately equal to that analog value. So rounding off means, let's say we have a value, let's say minus, 1 and 2. Let's say there are some value lying between this 1.5 threshold value. Okay, so above this value, let's say we will say the 2 volt, and below this value, let's say we will say the 0 volt, or you can nomenclature it as a 1 volt. Okay, so this is the quantization of the rounding of this value, and this is nothing but the digitization of this analog signal. So this is the one kind of, you can say, the quantization. So method of, sampling chooses a few points on the analog signal, and these points are joined to round off the value to near the maximum, or you can say near the stabilized value. This process is known as the quantization. I'm repeating once again. The method of sampling chooses a few points on the analog signal, and these points are joined to round off the values to near the stabilized value. This process is nothing but a quantization. Rounding off and truncation. Rounding off and truncation are the most important or typical techniques, or most important techniques, most important examples of quantization. These are the two most used techniques for the quantization. Now I've come to the encoding. Why we are going to use the encoding? What is the meaning of encoding? Right. So it is nothing but the converting the data, right? Converting the data, or providing security to the data. Converting the data, either the data in the form of character, right? Or you can say the symbol, or you can say the alphabet, or you can say the image, or you can say the speech, etc. Right? Into some, specified, into some specified format, so that the security can be provided. Okay? Why? We are the for secure transmission. For secure transmission of the data. Transmission of data. So this is nothing but the encoding. Right? What the decoding? Decoding is the reverse process of encoding, by which we can extract the information from the converted format. Right? So it is the decoding. Decoding Decoding is the reverse of encoding, right? Reverse of encoding, okay, which is which is to extract the information from converted format, right? Convert to second format. Now last discussion of today is analog as well as the digital signal. What is the analog and digital signal? Hope it is clear now. So any signal, either in the continuous in time, or continuous in value, or continuous in value, or continuous in time and value both, right? These are the signals are known as analog. Simple. How in the digital? Digital means discrete in time as well as value. If the signal are discrete in time and value, then you can say the signal is digital. So our next part of the discussion is we will cover in the next lecture elementary continuous time signal. Elementary continuous time signal. So thank you very much.